Our objectives for today's lesson are to understand the progression of the atomic model and to understand electron movement within Bohr's model of the atom. So this just kind of gives you an idea of how the atomic model has progressed. So our first one was back in 1898, J.J. Thomson developed what he called the plum pudding model, where he just had basically a bunch of positive stuff with some electrons kind of pushed into it like a plum pudding. That one lasted for a little while until Ernest Rutherford came up with his model of the atom called the planetary model. And we'll talk more about that one here in just a second. After the planetary model, Bohr, who was a student of Rutherford, kind of built upon Rutherford's model to complete his. And then finally, the most current one that we'll talk about later is called the quantum mechanical model. So let's take a look at the planetary model of the atom just a little bit. Here's a picture of what that looks like. And so Ernest Rutherford, he was doing his gold foil experiment, where basically he just put up a piece of gold foil and he shot it with positively charged alpha particles. When he shot it with those positively charged alpha particles, what he noticed is that most of the alpha particles just went straight through, nothing happened to them, but some of them became deflected. So they either bounced off and kind of deflected off to the left or the right, or some of them actually came completely back at him. And so what he discovered from that is that there must be something at the center of the atom that is positively charged. That's why it deflected the positively charged alpha particles, but that the rest of the atom must be empty space. And so he called that concentrated area of positive charge the nucleus. And so the nucleus is that tiny central core of the atom that is composed of the protons and the neutrons. And then he said that the electrons must just be distributed around the nucleus, and they're going to take up most of the volume. There were a couple of issues with Rutherford's model. In fact, it couldn't explain a couple of chemical properties that we see, one of those being the fluorescence of gases. If you've ever seen like a neon sign or even just the fluorescent lights that we use in the classrooms, that is caused by the fluorescence of gases. Also, it could not explain the flame tests that you're going to look at later on in this unit, as why do different metals change the flame different colors. So Niels Bohr, who was a student of Rutherford, he took into account all of that new data and tried to improve upon his teacher's model. And so over here on the right, these are some what we call emission spectrums. So here you see our fluorescent hydrogen. If we use what's called a diffraction gradient, it will actually break that light into each of these little lines. And so each element has a different emission spectrum. This is actually how astronomers figure out what stars are made of. Okay, so let's take a look at Bohr's model of the atom a little bit closer. Again, this is after he has taken into account some of that data to improve upon Rutherford's model. So now Bohr's model of the atom, we still have the nucleus. The nucleus has not changed, and that will not change. Now we just say that the electrons are found in specific orbits around the nucleus. So instead of the electrons just kind of being free-flowing wherever they want to go, now they have to be found on these specific orbits. Each one of these orbits has a fixed energy, and so we also call these orbits energy levels. So we have the n equals 1 energy level, n equals 2 energy level, et cetera, et cetera. And so the electrons have to be found on these orbits. They cannot be found in between. Much like if you have a ladder, people cannot stand in between the rungs of the ladder. You have to be either on the first step or the second step. So an electron can be in one of two different states. He can be in what's called the ground state, which is the lowest energy level available to that electron. That's kind of like his home where he wants to live. Or he can be found in what's called an excited state. An excited state is when the electron is in any energy state above his ground state. Now, these two terms are going to be very important when we're talking about the movement of the electrons. So make sure you understand ground state and excited state. So we can have the electrons moving between energy levels by either absorbing light or absorbing energy or emitting energy. So here's our first example. So here we see our ground state electron. He's in his house. He's going to absorb this energy. Okay, so we see this little arrow, that's representing our energy. So when he absorbs that energy, he's going to move up into a higher energy level, which we call an excited state. He does not like being up there. It's very, very unstable for him. So what's going to happen is he's going to move back down to his ground state. And when he does that, he releases that excess energy. So if you want to go from a lower level to a higher level, you have to absorb energy. If you go from a higher level to a lower level, you release energy. And depending on how far you move, you release different types of energy and different colors of light. This is actually how fluorescent lights work. So what happens in a fluorescent light is the electricity excites the electrons to a higher energy level by absorbing the energy when you flip that switch. The electrons are unstable at that higher energy level, so it wants to fall back to the ground state, and when it falls back to the ground state, it releases that excess energy as the light that we see. A couple more terms that we need to know. So the amount of energy that is required to move that electron is what we call a quantum of energy, and you can have different values for that. As we saw when you had a little bit longer trip back, you got a different color or a different amount of energy. That quantum of energy can be released as light, which we also call a photon. Remember, photo means light, so photon is light. And that again happens when the electron falls from the excited state to its ground state. And again, not all quantums are the same, as the energy levels are not all evenly spaced. So when you look at the hydrogen atom on the back of your reference tables, you'll see that the energy levels are closer together as you move up and further apart as you move down. So let's take a look at a couple of examples. So you'll find this chart on page 8 of your reference table. So our first question says, what wavelength of energy is given off when an electron moves from the n equals 3 level to the n equals 1 level? So what we're going to do is we're just going to use this chart. So we know that we're starting at n equals 3, so that's where I'm going to start. And I'm going to follow this down till I hit a dot. So there's my dot. Now let's see where it's pointing. Okay, so it is pointing to n equals 1, so that's the correct dot that we want to look at. Now if I follow it out, it's going to hit at our wavelength. So the correct wavelength here is 103 nanometers. Okay, let's do one more. So this one says, what color of light is seen from an electron transition of n equals 4 to n equals 2? So we're going to have to do the same thing we did in example 1 first, but then there's going to be one more step this time. So we want to go from n equals 4 to n equals 2. So here's n equals 4. Okay, so here's a dot. That one's going to n equals 1. That's not the one we want, so we're going to keep going. Okay, that one is going to n equals 2, so that's the one that we want. And so we see that it comes out to be 486 nanometers. So that's the wavelength that is being given off. However, it did not ask us for the wavelength, it asked us for the color of light. So that is going to fall somewhere here in this visible light spectrum. So we need to figure out where does it fall. Now we see that this is measured in nanometers and this is measured in meters. The easiest way to convert that is I'm just going to move my decimal 2 places and add times 10 to the negative 7. So I'm looking for 4.86 times 10 to the negative 7. Okay, so if we look in our chart here, we see that 4.86 is going to come between 4.2 and 4.9. So the color of light that's giving off is going to be blue.